Good morning, guys. It's Miss Johnson. You're maybe not even watching this in the morning, but it's morning for me. So I had recorded this whole video. I was super pumped about it. I was drawing at the same time I was talking, and when I watched it, there was no sound. So I am, just for today, going to talk over these notes while I'm not drawing it. But in future videos, A, they'll be posted much sooner than this one was, and B, I'll be talking and writing at the same time, so it'll be a little bit more dynamic. I just wanted to get this one out there so that you can watch it on Friday afternoon if you so choose. Okay, sorry again. But hello, welcome to Unit 1, Intro to Motion. I'll go off on more math routes as these videos progress and as we get into more of the unit. But calculus is all about motion, and again, I'll go off into rants about that. But one of the main things is when we're in motion, we're not just like walking in one direction at 3 miles per hour infinitely. We're stopping, we're starting, we're speeding up, we're slowing down, we're changing directions. So there's going to be a lot of not smooth, like beautiful curves, but these piecewise chopped up functions when we're talking about motion in calculus. So let me just go ahead and redefine or possibly define piecewise functions for y'all. It is a function that is defined on a sequence of intervals. That's what I've written down. But basically what that means is it's a function that acts differently for different groups of x's, right? The classic example, the one that every mathematician, every math teacher, every math student can think of is absolute value, right? Can y'all see my mouse? Here's open. When we do absolute value, we like created this weird symbol, this double bar for absolute value because it's not a like super nice function to write out. We could have written it out as a piecewise function, right? We could have said it's a function f of x which equals negative x when x is smaller than 0 and positive x when x is bigger than 0, bigger than or equal to 0, right? So in a piecewise function, there's two subfunctions. The subfunction negative x, I've drawn it in yellow. And this subfunction positive x, I've drawn it in blue. And when you graph it, you'll see that I like have a dotted line. I guess it's this way for y'all. Oh, wow, this is really hard for me. Okay, this way for y'all, right? I drew a dotted line in yellow, and then I only filled in, like I only care about the part that's less than 0, because that's what my piecewise function dictates that I care about. Let's get into a more beefy example. Nope. That's not it. Here it is. Example in detail. You'll notice that when I take notes, I use Greek alphabets to kind of delineate my thoughts. You don't have to do this, of course. It's just my personal note-taking system. Okay, so an example in detail, we've got g of x, where the first subfunction is negative x squared plus 1, and we're only doing negative x squared plus 1 when x is smaller than 1, right? And the second subfunction is 2x, but we're only doing 2x as the function when x is bigger than 1. Cool. So again, I graphed these in yellow and blue, and then I kind of so the yellow parabola opens down, the blue line is there, and then when I'm actually graphing this piecewise function in white, I'm tracing over the yellow line when x is smaller than 1, so everything to the left of 1, including 1, and to the right of 1, I'm tracing over the blue line. Seems good. These different x less than 1, x greater than 1 things, it's splitting up our domain, right? If you remember, a domain is the set of inputs for a function, so it's the x's we're allowed to plug into a function. And for piecewise functions, we're chopping up that domain and saying, oh, care about this function on this part of the domain and care about this other function on this other part of the domain. Cool. Say I wanted to plug in numbers to a piecewise function. All right, seems reasonable. We can either do it by plugging things into the actual function or looking at the graph. I like to plug things into the function because I'm not very good at drawing, so let's do that. If I wanted to find g of 0, I'd come over here, and I just plug in 0 to my function. But you say, Laura or Miss Johnson, there's two functions. Which one do I do? I say, okay, well, if it's x equals 0, 0 is less than 1. So I'm going to use that first subfunction. I'm going to use the quadratic. So I'm going to say negative 0 squared plus 1 equals 1. Boom. So g of 0 is 1. All right, say I want a g of 1. All right, well, I say, okay, if x equals 1, I go to my subdomains, and I look over here and I say, okay, well, is 1 less than or equal to 1, or is it bigger than 1? 1 is less than or equal to 1. So we're also going to plug 1 into this first subfunction, this negative x squared plus 1. So over here I say negative 1 squared plus 1, math, it's 0. Great, I'm going to move my face for a second. What if I wanted to plug in 2? All right, well, I say, okay, x equals 2 is bigger than 1. So I need to plug that into the second subfunction. So now when I'm doing my math over here, it doesn't look the same as the first two because I've plugged in 2 into the second function. So 2 times 2 is 4, g of 2 is 4. All right, so that is an example of a piecewise function in detail. And then the next and last thing we're going to do is say, okay, so we've seen 2 functions, piecewise functions so far. The absolute value one was continuous. We can draw it without picking up our pen or pencil or quill or whatever you're using. Stylus. The second example we gave was non-continuous. If we wanted to trace this graph, we would have to pick up our pen at x equals 1 and move it so we can keep drawing, right? So if we had kind of like a skeleton of a piecewise function where there's a constant a, like a mystery variable a, but we wanted to say, okay, this is a piecewise function, it's got 2 subfunctions. We want to plug in a number for a such that this piecewise function is continuous, right? How would we do that, right? So I whenever I start problems, I draw pictures. It makes it easier to think if you're looking at something. So I went ahead and graphed 2x squared minus 3, and then so that's the yellow line. Yeah, the yellow one. And then I filled in the parts that were less than 2 because my subdomain is x is less than 2. Nice. And then when I went to draw x plus a, I thought to myself, well, I don't know what a is, right? But I know that it's going to be a line with slope 1. So I kind of drew a couple until I found one that met at this intersection point, right? Because again, you can have a piecewise function that jumps, but right now we're trying not to jump. We're trying to be continuous. So I kind of drew a line that looked right, and I said, it's probably going to be x equals 3 or a equals 3, but let's see for sure. Because we're so interested in these 2 subfunctions meeting at the exact same point, like intersecting at x equals 2, our switchover point's x equals 2, so we want these 2 functions to be the exact same at x equals 2, I just plugged in 2 to the first one. So 2 times 2 squared minus 3 equals 5. And then I said, okay, I'll just set my second subfunction equal to 5 when I plug in that x equals 2. And I'm going to do another example after this, so if this is, a lot, that's all right. Okay, so when I plugged in 2 for the second function and set it equal to when I plugged in 2 for the first function, I got that a equals 3. Our picture was actually pretty good. And now, for the second example, now we've got 2 mystery constants, right? A and B are mysteries for our piecewise function f of x equals ax minus 3 when x is less than or equal to 2, or negative x plus b when x is bigger than 2. You might say, Ms. Johnson, you just said when problems are confusing, draw a picture. We can't really draw this picture yet because we don't know a or b, so we can't really pinpoint a line at any point. So we say, okay, in the last one, we wanted these 2 points to be equal where they intersected at the switchover point. So for this one, the switchover point is still 2. I'm going to plug in 2 to my first subfunction and then set it equal to plugging in 2 for my second subfunction. So again, I've plugged in 2 to my first one, a times 2 minus 3, and I've set it equal to plugging in 2 for the second function, negative 2 plus b. All right, I'm going to solve for b because it's the easier one to solve for. So now this white expression in brackets is like a true relationship between a and b. And then you say, okay, well, what's A? Say we plugged in 0 for A. If we plugged in 0 for A, that means B is -1. And then coming over here to this piecewise function box in yellow, we see that, okay, well, if A is 0, this first function was just -3 when x is smaller than 2. And if we plugged in b equals -1, this second subfunction is -x minus 1 when x is bigger than 2. That's a piecewise function. It's continuous. We've succeeded. Yay! Is that the only answer? Absolutely not. So down here, again, say we had chosen a equals 2 instead. That's fine. If a equals 2, we can plug it in and get that b equals 3. And then we can plug in those two a's and b's to our original piecewise function and get that f of x is 2x minus 3 when x is smaller than 2 and -x plus 3 when x is bigger than 2. That's also a piecewise function, and it's also continuous. So if our question said, find a and b such that this piecewise function is continuous, we would have succeeded either way. All right, guys, that's all I got for right now. I am going to sign off. It's 8:51 my time, so I need to log on for advisory, and then I will upload this video before our asynchronous time on Friday afternoon. And again, I'm not trying to slow roll you guys. I'll get the videos up by Sundays in future weeks. Thanks.